To start our lecture, last time what we have seen that various steps which are involved in designing of knuckle joint. Now we are going to see the further part of this knuckle joint. We have seen the major stress which are induced in the various parts of knuckle joint. And we have started from the single eye section and we have come across the double eye, then pin, and we have calculated the various dimensions which are required. Now, once you have find out all these dimensions, then major other stresses which are induced in the total assembly that we have to find out. Now here we have calculated the dimension of pin, and also we have calculated as a diameter of head of that pin by means of this empirical relationship. Okay, we are not going to consider the stress which are induced in that. Now we are moving further and we are going to check various other stresses which are induced in the all components of that knuckle joint. Now, what are that stresses which may get induced in the knuckle joint? That is various parts of that knuckle joint, including single eye, double eye, and pin. So, in case of pin, we have covered all the stresses. That is shear. It may get fail because of the shear, or it may get fail because of the bending, and that both the cases we have considered. But if you are going to remember, then we have seen in case of single eye and double eye that we have considered only one major stress which get induced in that component. Rather than we can say we have considered only one type of, that is tensile stress. And what about the others? That is whether we are going to consider the other stresses or not, that we are going to check. Okay. So first of all, we'll check the stress which may get induced in the single eye. And before moving to the single eye, by means of empirical relationship, we are going to calculate the diameter of that eye, that is fork eye. And that DO, that is outer diameter of that eye, that we are going to calculate as a 2 of D, twice of the D, where D, small d, we have used for the pin diameter. Okay. So by means of this, we are going to calculate that dimension. But when we are going to consider other type of stress, that is tensile stress may get induced in the single eye. At that time, we consider this tensile stress and we have calculated the dimension here. So what we are going to see is that this tensile stress which may get induced in the single eye will create the tensile stress because of the tensile force which we are going to transmit to the through the single eye. Then here, as we are going to use the formula everywhere in the total design procedure, that basic formula which we have used is as a design tensile stress is equal to tensile force divided by resisting area. That is nothing but stress is equal to force divided by area. Which type of stress we are going to consider? That stress, that design stress, we are going to consider value, and later on that type of load which is coming in that component, that we are going to consider. Here we are going to consider tensile failure. That's why tensile stress is considered and tensile force is considered. Okay. And whatever may be the area, cross-sectional area, which is going to resist to that type of stress, that cross-section area we are going to consider in that component. This formulae we can modify for the calculating load, that is tensile force, that is equal to, just what we are going to do is that we are going to take the resisting area to the other side and we are going to calculate the force. Okay. So tensile force is equal to resisting area multiplied by design tensile stress. That basic formula we are going to use. Now here you can see that the P, that convention which we have used for the tensile load, is given by resisting area for the tension multiplied by allowable tensile stress, that is design tensile stress, which we are going to consider. And that can be mathematically written as P is equal to. Now, while we are going to calculate the resisting area, so which area you are going to consider? This area which we are going to consider is the area when we are going to cut that eye, then whatever may be the projected area that in this diagram it has been shown by the hatching line. Also, it has been that resisting area name has been given to that resisting area, but only one arrow has been shown. There are two such areas which are undergoing for the tension, which are resisting to the tension. Okay, so when situation will happen as like shown in diagram, that the eye is going to cut in two sections. Okay, so which area will resist to it? That is the hatching area, or the area which has been shown by the red hatching lines. So that area we have to calculate, and the stress which is induced in that, that is the tensile stress. Okay, so you can see here, while we are going to calculate that resisting area, one can see here that the d is the small d is the diameter of that hole which has provided in that eye for inserting the pin, and do is the diameter of that eye, outer diameter of that eye, whereas T1 we have considered as a thickness of that eye. Now, while we are going to calculate the area is here in this case height multiplied by width. Okay, and if you are going to multiply it by 2, it will become twice of that area. Okay, because two times there are two areas, those who are resisting it. But simple way, can we calculate the distance here that will give us the total horizontal length of that area? So simply if you are going to do that d2 minus d, then we are going to get d2 minus d. If you are going to do, then what we are going to get is the length, total length of that area. Okay, and height is t1. So when we are going to multiply by d0 or do minus d, if it is multiplied by t1, it will become the area which has been shown here, right? It includes both the sides, because do minus d is not dimension of one side, it is dimension of both the sides. So do minus d multiplied by t, that will be the area which we have calculated here, and which is multiplied by t, and then afterwards by means of sigma t, that is design tensile stress. Okay, in that component, then easily we can calculate value of p either, or value of sigma t also. If you are knowing p, you can calculate sigma t, and if you are knowing limiting value of sigma t, you can calculate p, because do and d, also t, we have calculated already. We are knowing it. Just we are going to check here whether that stress level is below the allowable stress level or design stress level. And if it is below, then we are going to consider that whatever may be the dimensions which we have decided, that dimensions are correct. Are you getting me? So don't omit this step also. Once you have calculated all the dimensions, then one can think that can I omit this step? Why to go for this step now? Already we have calculated all the dimensions. Then what is necessary to consider other type of stresses? It will become wrong step. Okay, our design may not be safe in that case. Why? Because we have not checked the other probabilities which are there. That is, this I may get fail in tensile, which we not considered initially. Okay, or next step we are going to see that this I may get fail in shear. That is, that pin hole, that total diameter of that pin is going to cut out that I section. So in that case, it will be sheared out, right? If that material is not sufficient strong, if it is not capable to sustain that shear stress, then definitely that pin will shear out all the part which is coming in the region of that pin from the eye, which has shown in this diagram. Okay, with pin, this all area will come out. Now we have to check whether that stresses which are induced as a shear stresses are within the design limit or not. So for that, what we have to do? Again, we have to use basic formulae. That is, stress is equal to force upon area. Just we are going to convert it into, by taking area to the stress side, as a force is equal to area multiplied by stress. Now area which we are going to consider, and stress which we are going to consider. Now stress which we are going to consider here is the shear stress. So shear stress value we have to consider here, and according to that, we have to modify the formulae for the stress. Now, up till now, do you have any question? Am I audible to everybody? Hello?
Yes, sir.
Yes, sir.
Okay.
Yes.
Okay. Okay. Right. Do you have any question up till now? If you don't have question, then let me ask a question. So now here, if we are going to consider the tensile stress, sorry, shear stress, then area, can you calculate just area? Up till now, you are knowing how to calculate the area which is resisting to that type of stress. Now here, uh, resistance which is occurred, that is what? Resistance to the shear. So can you just calculate area? Anybody of you? Will you please, you can write in comment box. Just I want to know resisting area for the shear. Hello? If that part is going to get shear, then which area is going to resist to that shear? Hello? Let me tell you one again, that what we can say the imagination part it is, that when we are going to calculate the dimensions or we are going to check the stress in particular component, then we can consider that component is weakest component in that total assembly. For sake of simplicity, we can consider that it is made up of soap. I repeat, आपण ज्यावेळेला कुठलाही कंपोनंट डिझाईन करून त्याची कंपोनंट काढत असतो, त्याचे डायमेन्शन्स काढत असतो, त्यावेळेला असं कन्सिडर करायचं की तो जो पार्ट आहे तेवढाच पार्ट फक्त साबणापासून तयार केलाय. ओके, आणि बाकीचे सगळे आहेत ते स्टील पासून तयार केले. आणि समजा आपण त्याच्यावर जर लोड लावला तर काय होईल? ऑब्वियस आहे ह्याच्यामध्ये की दोन एंड असलेला एक फोर्क आहे आणि एक सिंगल आय असलेला फोर्क आहे. तो जर एकमेकाला जोडला आणि त्याच्यामध्ये पिन टाकली आणि सिंगल आय फक्त साबणाचा बनवलाय, बाकी सगळे लोखंडाचे, काय होईल मग? साबण तेवढा स्ट्रेस घ्यायला केपेबलच नाही, तो शिअर आउट होईल तिथनं. मग तो शिअर झालेला एरिया किती असेल तो आपल्याला कॅल्क्युलेट करायचा आहे. ह्या केसमध्ये शिअरिंग एरिया, the area which is resisting to the shear is nothing but the area which has been shown in this diagram by the hatching lines. Okay, and shear is not occurring to the one side, it is occurring at both sides. So while we are going to calculate the area, at that time we have to take either 2, that is both the side areas are going to cut out, and then we have to multiply it by the dimensions. So the hatching line which has been shown here, that dimension, now horizontal dimension of that area is calculated by RO minus R, where RO is the radius, outer radius of this eye, and R is the radius of that pin or inner circle. Now we have not used this convention as RO and R. What we have used is the DO and D, that is the outer diameter of eye, and D is the inner diameter of eye, which is equal to the diameter of that pin. So that value, to calculate that value RO and R, what we have to do is that we have to write DO divided by 2, that will become R, radius of that outer circle, okay, minus D divided by 2, that will become radius of inner circle. Why? Because we are going to consider at one side only, dimension which is required is from one side only. Okay, so this dO by 2 minus D by 2, that will give us the horizontal dimension of this shaded area. Okay, now we have to take vertical one. Vertical is the thickness of that eye, and that is T1, that already we have used. So area will become that DO by 2 minus D by 2, okay, in one bracket, multiplied by T1. That will be the area of one side, which has been shown as a by the hatching lines here. But the shear is taking place to the both sides. That's why we are going to multiply this area by 2. That is what has been shown in the next slide. This is, you can see here, this value of P, that is the load, tensile force which we are going to apply. Now, though the force is applied as a tensile, it is going to shear out it. Okay, so P, the applied force is going to remain same, is equal to resisting area. In here, it should be shear, not tension. Okay, resisting area in shear multiplied by allowable shear stress. Now, if you are going to write it in mathematical form, it will become P is equal to 2 multiplied by, into bracket, DO, that is the outer diameter of that eye, divided by 2 minus D divided by 2 into T1. That will be the area, resisting area, multiplied by tau. Tau is the design shear stress. In this case, already we have calculated dimensions. DO we have calculated, D we have calculated, T1 we have calculated. Then in this formula, if you are knowing the design shear stress, you can calculate force P. Or if you are knowing the P, you can calculate design shear stress, value of design shear stress. And once you got that value of design shear stress, just we have to check that whether it is less than what we have considered, what is given in the problem. If the shear stress value is 100 megapascal, and by means of this formula, the value which we are going to get is 90 megapascal, then definitely we can say the dimensions which we have choose are safe. That is, design is safe. Okay, while solving problems, we have to write this comment also, that according to this formula, the value of tau which is coming is less than the allowable or design shear stress, and hence the dimensions which we have calculated are safe or design is safe. So while we are checking the exam papers, then we are going to check whether you have written this comment or not. So you have to take care that once you complete this step, below that step you have to write, hence design is safe, as the calculated shear stress value is less than the design shear stress value. Getting me? Now this formula can be simplified. This DO by 2 minus D by 2 that can be written as a dO minus D divided by 2 because uh, denominator is same. This 2 will get cancelled, which were multiplied for the doubling of that area. So this 2 will get cancelled. And for simplicity, we can write this formula as P is equal to dO minus D multiplied by T1. And that will get multiplied with design shear stress. Using this equation, you can check value of tau and check whether it is less than the allowable or design shear stress value so that the total design will be safe. Okay. Uh, Everybody is getting? Please give me feedback in chat box or
Yes,
your written something. Yeah. Yes. Yes. Wow. You have given answer for the area. T1 into dO minus D by 2. Good. And doubling the area. Very good. So you are getting the things which you are learning. Very good. Uh, shall we move further? Yes. Now we are going to consider the crushing stress also. Most of the time, if you are going to see this knuckle joint, then this knuckle joint gets wear out, and that pin will become loose inside that total knuckle joint, and hence most of the time this knuckle joint is replaced. Now, this case doesn't have any meaning when we are going to consider it in case of tractor and trolley. Getting me? Unless and until that whole joint is not going to break out, we are not going to replace it. But in some critical applications, some machineries where these knuckle joints are used, in that case, we are going to replace this total knuckle joint if the dimensions or elongations take place or wearing of that pin as well as that single eye or double eye is going to take place. For example, we can say in case of mm, suspension of vehicles, this knuckle joint is used. And in that case, if that parts get wear out, then noise is generated because of that part, and hence it will get replaced. Okay. So now here we are going to consider crushing stress also. The crushing stress which is induced because of the pin which is going to press against the eye, and that pressing creates the crushing of that pin as well as that eye. Now area which is coming under this crushing, that area is important because what we have seen is the stress is equal to force divided by area. Force is going to remain same, that total P which you want to transmit from one end to another end of this knuckle joint. Now area which is undergoing to the crushing. Now it is circular area, but for sake of simplicity, as we know that we are having a habit of neglecting something and considering whatever maybe we want. Then here we are going to consider that area which is actually basically curved area. That curved area has a straight part. Okay, because to calculate simply we have to make the calculation simple, and hence we are going to take the projected area, that is actual regular triangular sorry, that squared area. Okay, rectangular area you can say. It is not square. Basically we don't know whether the t and all the dimensions are same or not. That's why we are going to consider the projected area, that rectangle, and the force is the P. So again, we are going to modify that formula as P is equal to resisting area for the crushing multiplied by the allowable crushing stress. Now again, I'm going to repeat that crushing stress value is considered as a compressive stress value only. Okay, separately we are not going to use the what will be the crushing stress value. That will be considered as a compressive stress value only because basically crushing is nothing but the compression is taking place. And if it is going to have relative motion between that two parts, then it will go towards the friction, and friction has its own theory, and that using that theory we can calculate whatever may be the friction which is taking place, and how the wear will take place, what will the wear rate and all that. But here, as a designer, what we are going to consider is that the crushing is nothing but the pressure is applied, and that pressure when we are going to apply against any component or any part, then it will be creating compression. So that sigma C value, that is crushing stress value, we are going to consider it as a compressive stress value only. Okay, and uh, now here we are going to calculate what will be that area as well as the value of crushing stress. Now, while we are going to calculate this area, can you give me, this is very simple area to calculate. How we can calculate this area? That is horizontal dimension multiplied by vertical dimension. Horizontal dimension will be the diameter of that pin, that is D, and vertical dimension is T1. So D multiplied by T1 is the total area which is undergoing to the crushing, and it will get multiplied with the design crushing stress. So formula will become P is equal to area resisting to the crushing multiplied by allowable stress, allowable crushing stress, and that will become P multiplied by whatever area we have calculated, that is D into T1 multiplied by sigma C. Sigma C is the value of crushing stress. At this stage also, somebody has given answer. It's good, Omkar. Now, at this stage, what we are going to calculate, if you are knowing the value of P, because already D value we have calculated, T1 value we have calculated. Sigma C value, if we are knowing from the material property, we can put that value and we can calculate P. Or if we are knowing the P value, that is force which has to be transmitted, then we can calculate value of sigma C. And here we have to check whether that sigma C value is less than whatever may be the design compressive stress or design crushing stress. Okay, so value of that sigma C, if it is less, then we can write comment that design is safe. If it is higher, then what we have to do? That case we have not considered. If the value of sigma C which we are going to get by this formula is higher than whatever we have assumed, whatever we have calculated from SYT, that is ultimate tensile strength value, and using factor of safety, then what we have to do? Step is that we have to again go back and we have to uh, recalculate the dimensions. That is, just we can change the dimensions. Changing means again we have to increase the dimension. There is not any question of decreasing the dimension, because stress is going to increase. It means that resisting area is not sufficient. That's why we have to increase the dimensions. Okay. Generally, it doesn't happen. If that part is safe and in a shear, in tension, then automatically it is safe in the compression or crushing stress also. But we cannot neglect the possibility that the value of crushing stress may get increased. Just we have to check. We have to go through that procedure. Okay. So we cannot leave this step. We cannot omit this step, but we have to check it. And if the value is coming higher than design crushing stress, then we have to again go for the redesigning of component, redimensioning of that component. Okay, that's what we are going to do at every stage, not only this stage. At wherever we are going to get that higher value, from that stage only, we have to go to the initial stage and we have to start the redesigning of that component according to the value which is coming. Okay, of that particular. Here it is crushing stress. It may be in shear. It may happen in tension also. So we have to go for the redesigning. Now, next part, we are going to see that we have to check various stresses which may get induced in fork also, that we have seen in eye. Now we have to check whether that stresses which are induced in the fork side are within the limit or not. Now here you can see just somewhat I have modified the diagram that further part towards the rod side that has not shown here. I have concentrated only on the two eyes of this fork. Now, while we are going to consider that tensile stresses which are induced in this fork eye, then which area is going to resist that tensile stress? That area is important because sigma t, that is the tensile stress value, design tensile stress value more specifically, is equal to force divided by area. So while we are going to calculate that area is of both the eyes. Okay, that's why 2 is coming there. Multiplied by DO, that is the outer diameter of that double I4. Okay, minus D here, not D1, it is D. D is the diameter of that inner circle. Okay, so that will be the total area. And as there are two eyes, that's why 2 is multiplied for that. Multiplied by the thickness of that 4. Thickness we have considered as a T2. So here the value of stress will become force which has induced, force which we have to transmit, divided by 2 into dO minus D multiplied by T2. Finally, I'm going to provide all the formulas in one table only. Over there, all the corrected formulas are there. So P is equal to, now we are just modifying this formula as P is equal to 2 multiplied by dO minus D into T2 multiplied by sigma T. Okay. In this case, we have to just check whether this sigma T value is less than the allowable value, that is design stress value. Next, we are going to consider that the fork is fail in shear. Now, as already I have told you that while we are going to design such type of components, we have to consider that that component is the weakest component in the total assembly. Okay, and hence if the pin is strong, I is also strong, and if we apply the tensile force from both end of that knuckle joint, then definitely it will get shear out. It will shear, that pin will shear to the that fork. And the shearing area, that area is important. We have to calculate that area. Okay, force of shearing is same as a P. Now in this diagram, you can see that, by the way, am I audible to everybody? Hello?
Yes, sir. Yes, sir.
Okay, okay. Now we have to calculate that shearing area. Now, uh, as the area has been shown by the hatching lines, just if we are able to calculate one area, then we can multiply it by means of the number, as the numbers are there for the sharing. Wherever the sharing is taking place, that many numbers we can multiply. Okay. So while we are going to calculate the total area of sharing, okay, it will become 4 because in one eye from both sides that area is going to share out. Okay. And as we are going to have two eyes, that's why 2 multiplied by 2 will become 4. So 4 times the sharing area, because sharing is taking place at 4 places, 4 areas. Are you getting me? Do you have any question? Do you have any doubt at this place? You are free to ask. I'm saying that sharing is taking place at 4 places. Is it right? Yes. Which are that 4 places? Can anybody give answer? Which are that 4 places where the sharing is taking place? All that 4 places as shown in this diagram. Okay, two are shown towards the fork side, and two are shown towards the pin side. But that total surfaces are the surfaces where the shearing is taking place. Okay, now can we calculate value of one area only where the shearing is taking place? That is d2 minus d1 divided by 2, where d2 is the outer diameter of that eye, double I, minus d1 is equal to the d is the diameter of pin. Okay, divided by 2. Why? Because we are going to consider the horizontal length only, not both side length of that circular part. That's why divided by 2, multiplied by t1, that is the thickness of that fork. Okay, so once you are able to calculate this area, then shear stress value can be easily calculated, force divided by area. Now this, it is mathematics. 2, if you are going to divide to the 4, it will become 2. That's why area will become 2 into d2 minus d1 multiplied by t1. Okay, so again thickness and diameters we have to consider of that fork as well as the pin. So the allowable shear stress value which we are going to get from this formula, finally the formula has written as P is equal to 2 multiplied by dO minus D into T1 T2 multiplied by shear stress. Okay, now here somewhat confusion is there in T1 and T2. Basically we are used T2 as a convention nomenclature for the thickness of that fork side, and T1 we have used for the eye section. Okay, single eye section. So the final formula is correct. That is P is equal to 2 into dO minus T into T2 multiplied by shear stress. And this shear stress value, we have to check whether it is less than the design shear stress value. Okay. Now, as we have checked that all possibilities, that is tension, shear, we have to check the possibility of crushing also, as we have seen in case of single eye. Now, in case of double eye, also the crushing will take place. And that crushing area, as we have considered, though it is circular one, we are going to consider it as a straight, okay, rectangular area, and we have to calculate that rectangular area. Now, this rectangular area naturally we will get multiplied by 2 because two eyes are there, and area of that hatching part, or that where the hatching is we have done, that area we have to calculate for one side only, and that will be outer diameter, sorry, inner diameter of that eye, that is the pin diameter, d1 is equal to d multiplied by t2. T2 is the thickness of that fork side eye. Okay, so area can be simply calculated. Then crushing stress value sigma c is equal to p divided by area. Area is 2 into d1. D1 is equal to d small d multiplied by t2, that is the thickness. Okay, from this, if we are going to get the sigma c value as a less than whatever may be the design sigma stress, sigma c value, sigma crushing stress value, then we have to say that the design is safe. Okay, and finally, all these formulas are formulated in one table, are mentioned in one table. All the steps in this design. Okay, so we can go through this, and later on we'll see the problem to the next lecture. What is time now? Hello, can anybody tell me time?
11:53, sir.
11:53. So shortly we'll see the table. Okay, in this table we can get all the steps which are involved in this design. Then the criteria for the failure which we have considered at that place. Also the equation, mathematical equation which we have derived. Okay. And finally, what value we are going to get from that step, from that criteria that is written in this table. Now, step number one is that we are going to design the rod diameter. Okay. And that extended part of that rod where we are going to manufacture as a single eye or double eye. That is the enlarged part of that rod. That two dimensions we are going to get from the first step. And second dimension, that is D1, that is enlarged diameter of capital D1 again, enlarged diameter of that rod, that we are going to calculate by means of empirical formulae only, as already we have discussed when we have gone through this step. Okay, so we are going to consider first step as a design of rod, where we are going to get the dimension of that rod as a capital D, and that further elongated or modified diameter of that same rod towards the fork section or eye section, that is D1, okay, capital D1. That two values we are going to get. So which criteria we are going to consider here? That the failure criteria which we are going to consider is the tensile one, okay. And from that, the equation which we are going to use is force is always given by area multiplied by stress. So force is P, area is pi by 4 D, capital D square, multiplied by sigma T, that is the design tensile stress value. Okay. From this, we can calculate this capital D. And by means of empirical formulae, we are going to calculate the extended part of that rod, that is D1. And it is equal to 1.1 of rod diameter. Okay. Then second step, we are going to consider deciding thickness of eye and fork end. Okay. So while we are going to consider that thickness of fork section and eye section, single eye section and double eye section also it is called as, we are going to use the empirical relationships. T1 is the convention which we are going to use for the thickness of single eye, and T2 is the convention which we have used for the thickness of double eye, and it is given by T1 is equal to 1.26 of rod diameter and T2 is equal to 1.75 of rod diameter. At this step, we are going to get value of T1 and T2. Okay. Then we can move to the further step, that is step number 3. That is, we are going to decide the dimensions of pin. For deciding these dimensions of pin, we are going to use shear as a criteria. Obviously, shear is taking place at two places of that pin. That's why we are going to consider double shear, which is taking place for that pin. And second criteria we are going to use as a bending for that pin. Bending may take place of that pin which we are inserting in between that fork and eye. Now, while we are going to consider the shear, at that time force is equal to resisting area multiplied by stress. Now, the resisting area which we have calculated at that place is 2 multiplied by pi by 4 small d square, where small d is the diameter of that pin, and multiply by sigma s, that is shear stress value, or here you can use tau as a convention also. Okay. So from this formulae, we can get diameter of that pin, that is small d. And just we are going to check whether this diameter of pin is sustaining the bending stress, that is sigma b. So we are going to use the formulae for calculating diameter of that pin, that is equal to cube root of 32 divided by pi sigma b multiply with p divided by 2 in bracket t1 by 4 plus t2 by 3. This formula is used for checking the bending stress. From this, if the value of d which we are going to get is less than the value of d of previous formula, then we are going to keep that highest value. If that D which we are going to calculate from the second formula is higher than the first formula, then we are going to keep again the D which we have calculated from the second formula, whichever may be the highest. That value of small d we are going to keep for in our design. Okay. Then further we are going to calculate the diameter of head of that pin, and diameter of that head we have mentioned as a D1. So D1 is equal to 1.5 of D. That again we have calculated from the empirical formula. No stress criteria we have used. Okay. Here again comment has been written. Choose higher value of both. That is from that both. Whatever may be the higher value which we are going to get in the stress. That is either it is double shear or bending. Now we are moving to the fourth step. In that fourth step, we are going to calculate or we are going to check the stresses in single eye section. Okay. And which are the stresses? That tensile, shear, and crushing. Now from the empirical formula, first of all, we are going to calculate the outer diameter of that single eye, that is DO, which is equal to 2 twice of that pin diameter. Then we are going to use the tensile criteria, and we are going to calculate the P, force is equal to area multiplied by stress. So the area which is undergoing for the tension is DO minus D multiplied by T1, that is the thickness of that eye, multiply with design tensile stress value. Just we are going to check whether this tensile stress value is less than the design tensile stress value. Okay. Then we are going to consider shear failure of that single eye. Then the shear failure, while we are going to consider the shear failure, at that time force is equal to again area multiplied by stress, shear stress. That's why P is equal to DO minus D multiplied by T1, where T1 is the thickness of that single eye, DO is the outer diameter of that single eye, and D is the inner diameter or pin diameter. And here we are going to check value of shear stress. If it is less than the design shear stress value, then we are going to consider that dimensions are safe and design is safe. Then afterwards we are going to use the crushing criteria, where the crushing stress, if are multiplied with the area, will give us the capability of sustaining that force. So force is equal to D into T1. D is the inner diameter of that single eye. T1 is the thickness of that single eye, multiply with crushing stress value. And from this formula, we are going to check whether that sigma C value is less than the design sigma stress or sigma C value. That is the crushing stress value. Okay. Next, fifth step, which is last one. Same way as we have done in case of single eye, we are going to do for the double eye. That is, we are going to check the rest of the possibilities where the failure may take place. And that is in tension, shear, and crushing. Now, same formula, that is force is equal to area multiplied by stress. Just we have to calculate the area which is undergoing for the tension. That area is equal to 2 into DO minus D. DO is the outer diameter of the fork in eye. D is the inner diameter of that pin, and T2 is the thickness of that one side of that fork. Okay. So from this, we are going to calculate value of sigma T. If it is less than the design tensile stress value, we are going to consider all dimensions are safe. Then we are going to consider shear as a criteria, where we are going to calculate value of P, and from this formula, we are going to calculate the shear stress value. If it is less than the design shear stress value, then design is safe. Then for the crushing, as we are going to calculate the area which is undergoing to the crushing, that circular one, we are going to convert into straight area, and we are going to calculate value of sigma C, that is the crushing stress value. If it is less than the design crushing stress value, then design is safe. If you have understood everything, just what we have to do is that you have to go through this chart. In case of quarter joint also, I have provided that chart. In case of knuckle joint also, I have provided that chart. So that chart only is sufficient to understand various steps which are involved in the quarter joint as well as in knuckle joint. Okay. Do you have any doubt? Am I audible? Hello? Any one of you, please.
Yes, sir. Yes, sir. You are audible.
Okay. Do you have any doubt now?
No, sir.
No. Okay. So can I move further for the presenting?
Yes,
Yes,
sir.
sir.
Okay, sure. I will take presenting within a very short time. Just give me 2 minutes. 7 comments are there. Okay. Uh, where I can write it. Just wait. Don't leave meeting. Okay. Roll number third. I'll take from roll number one. 14 is present. Fourteen is present. 54. Then 39. Then 23. Then 1, 3, 4, 5, 6, 7, 8, 10, 13, 10. Okay, I have taken present. Now you can leave class. Thank you. Thank you for listening.